Hello there, and welcome to our video presentation for Physics 110, General Physics 1. As I mentioned in class on Friday, September 22nd, we won't be meeting for our physical class meeting on Monday the 25th. Instead, you're tuning in to watch this video presentation of what I had intended to cover that day. I'm using a technology called Swivel. It's going to follow me around, so just so you kind of get used to it, if I move left and right, the camera is going to pan with me. I hope I've set myself up on the whiteboard so that my writing will be a little clearer and more distinct, and hopefully my audio is being captured adequately so that you can hear. Of course, you have the benefit while watching online that you can pause, fast forward, if you wanted to skip over something, and rewind if you needed to hear something again. So I hope you'll take full advantage of that to make sure you've maximized what I'm covering today. And what we are covering is a continuation of the equations governing motion. We looked last class at developing a series of equations that connect the 5 properties of the motion of a body: position, initial velocity, final velocity, acceleration, and time. Again, those are listed in a table on page 117 in your textbook, and that list might be helpful as we go through a series, a couple more examples today in this video. So we did 2 examples at the tail end of our class where we looked at a ball being accelerated, and we found its speed and then the distance that it had traveled. Let's change up to a new example now, again with the laws of motion here. So I want to start with a train summits a hill moving at 18.8 meters per second. Okay. After descending downhill for 2,000 meters, all right, the train is moving 30.8 meters per second. How long did it take the train to reach the bottom of the hill? So you have a little diagram here, right? Your train has come up over the hill initially at 18.8 meters per second, and then as it comes down the hill and it reaches the bottom down here, its new speed is 30.8 meters per second. All right, and that distance, assuming the track distance, is the 2,000 meters. So the parameters that we know are the initial velocity, the final velocity, and the distance. What we're after is, okay, again, we know initial velocity, final velocity, and distance, which is x, okay? What we want is the time. How long did it take? So if we consult the 5 equations in table 6.1, we find one of the equations is x equals v0 plus v final over 2 times t. So that's average velocity over time. So we can solve this equation for the time. So the time would be, we would multiply the 2 over to the left side, 2x, and then we would be dividing by the sum VO plus VF. So that's 2 times 2,000 meters divided by 18.8 plus 30.8 meters per second. And when you just plug that in, you get 80.6 seconds. So a little over a minute and 20 seconds for the train to make this descent down the tracks, 2,000 feet down the tracks. Okay. We could have also been asked about the acceleration of the train. Again, these are all connected, these 5 properties. But you get the idea now. Once you know, as I was saying last class, once you know any 3 properties, you can find the 4th through one of the equations, and then subsequently you'd be able to connect it to the 5th property ultimately through a different equation. Okay? Now, before we move on to sort of the next category of problems, I want to take a minute to talk about signs and sign conventions. All right? Some problems give us, as the person doing the problem, they give us the prerogative to establish our own what constitutes plus and minus for direction or for velocity or for acceleration. And so this, can lead to a confusing situation, because one time you might be doing a problem and you might think of up as being positive, but the next time it might make more benefit for that to be negative. Or maybe a little more appropriately would be to say moving to the right would be positive one time, and then moving to the left would be positive in another problem. Okay, so you can get a little bit, off kilter. What you really want to remember is that these are all defined relative to each other. Okay, so the signs of x, v, and a, position, velocity, and acceleration, are relative to one another. And you really need, again, a diagram can be very helpful. Right? So if we consider a person who throws a ball upward, this ball ultimately, is going to go up and then come back down. Right? Throughout the process of this ball moving, actually, we're going to see that there are some different sign connotations here. So now where the ball was released would be defined as our x equals 0, our position equaling 0. So during this entire segment, first segment of the ball going up like this, the position is positive, right? The velocity is positive, right? But the acceleration is negative, because the acceleration, as we're going to move into our next section, is gravity's pulling down on the ball here. And so it would be working to slow the ball down. At the summit, when the ball is right up here at the peak, okay, x is still positive. The velocity is now 0, and the acceleration is still negative. All right? So the ball goes up, and right at that exact moment when it's stopped, it has 0 velocity. Now coming down on this side over here, our x is still positive. We're still above our initial point of release of the ball. Now our velocity is negative, and our acceleration is negative. Okay? And then there is one more small section we could consider. The ball could go below the point where we released it at. Right? If I release a ball right here, it's about 4 or 5 feet off the ground. There's potential that the ball can go below that. So finally, in that section, we would run into the case where x is negative, the velocity is still negative, and the acceleration is negative. Right? So we see in this case here that the only thing that's really consistent is that the acceleration is always negative. All right? It's working against the direction of the positive direction as we defined it for position. Right? So we defined position as positive, the upward direction on this diagram, and so acceleration is working against that. When the velocity is going in the direction, all right, that we define as positive for direction, it's positive. And when the velocity is against that, that's when it's got a negative sign. All right, so the sign conventions can be a little bit confusing at times, but a diagram can go a long way towards helping you establish a consistent set of signs throughout a problem. Okay. Now this little example of a ball being thrown upwards, which everybody certainly can understand that, I hope, is a great intro into, or a great segue into our next topic, which is the concept of gravity and free-falling bodies. Okay. So, in reality, we know that there is resistance offered to the movement of any object through the air. Call it air resistance or friction. We learned a little bit about friction in our previous chapters on translational equilibrium back in chapter 4. Okay, but in the absence of that, if we ignored it, or if it just wasn't there, in a vacuum, if we made a vacuum chamber and pumped all the air out, there would be no air to resist it. So in the absence of what we call air resistance, which is really a form of friction, okay, all bodies fall to Earth. Okay, with the same acceleration. Fall to Earth with the same acceleration. Okay. This acceleration is, of course, due to gravity. All right. So gravity, depending on where you measure it on the surface of the Earth, is slightly different. And maybe you've heard of this, that the gravitational pull is a little bit less the further you get from the Earth's center. So on mountain peaks, some high mountain peaks, it might be ever so slightly less. But for the most part, on the face of the planet Earth, gravity is you're not going to notice a significant difference. Now, on other bodies, like the moon, or if we went to other planets, then you would absolutely have a different feel for the acceleration due to gravity. Okay. Now, for our purposes, okay, we will use gravity equals 9.80 meters per second squared. Okay, or 32.0 feet per second squared as the accelerations due to gravity. Okay? They're, again, slightly different if measured in different places on the planet here, but for our textbook, we're committing to using these two versions of G. This allows us to work in the metric system or in the American system, whether we're using G meters or feet. Okay, so this becomes then the A. In other words, G is A for a body in free fall. All right, free fall would be any object above a surface that is, going to come down towards that surface. That object is accelerated downwards towards the Earth with one of these rates, either thinking of it as 9.8 meters per second squared or 32 feet per second squared. So this is the concept of free fall. Okay. We have to be careful about the sign again. All right. If we consider, all right, so if we think of the upward direction as positive for x, then g equals the negative 9.8 meters per second squared. But if you're going to think of where the object is released from as 0, and if you're going to, if moving down is, as you'd want to think of it, positive for x, then your g is the positive version of 9.8 meters per second squared. Right? So it's relative to how you decide to think of position, all right, in your system that you're working with. Don't let it become a point of confusion. Just understand that, you know, sort of putting the cart before the horse here. You can't define the sign of gravity until you've decided what's positive for your direction in your particular system. Gravity is always acting in a downward, okay, towards the Earth's surface. But, like I said, if you choose to think of moving downward as positive direction, then gravity is considered to be positive. Okay? Now, this just allows us to use, as I said, g in place of a in any of the equations that we have been using so far in this chapter. So let me go through a couple more examples of equations of motion where now we'll simply be talking about a body that is falling, all right, and you know, we'll be able to solve for various parameters. Okay. So the classic approach to a lot of these problems is to consider a ball, right? A lot of balls get dropped here. So a ball is dropped, okay, from rest. Remember what that means. It's sort of a key word, right? From rest. How far does it fall in 4.0 seconds? Okay. So, you know, if you dropped your ball, you're on the top of a cliff or whatever, whoa, down. How far will it fall in 4 seconds? So what's defined in this problem? The time, 4 seconds, is known. The initial velocity is known, right? That's the key words, dropped from rest. And then gravity is equal to the acceleration of this object. So in the previous example, well, it didn't apply in the train. If you look back to last class, the acceleration was defined for the examples that we did, and it was listed out. But now if you understand that the ball is falling, or whatever object is in free fall, that is defining the g, or the rate of acceleration. Okay? What we want is x. So we want to look for an equation that ties together time, initial velocity, acceleration, and x. And the equation that does that is the position equation. X equals v0t plus 1/2 a, but we can now substitute g for a into that equation. All right? A lot of times, another change that we make in this equation is we tend to think of this as y. All right? Usually we think of up and down as a y. So it's just the same. We're just substituting a different direction. Instead of moving horizontally, that's what we think of as x. We can think of this as vertically, so y. So how far does our ball fall? Well, we had 0 meters per second times the 4 seconds. That won't matter. Plus 1/2, 9.8 meters per second squared, times the time, 4 seconds, which needs to be squared. So 4 squared, 16, times 9.8, divided by 2, 1/2. the ball will fall 78.4 meters. Okay. Now in this problem, the sign didn't really matter so much. Was it positive or negative, right? I'm just saying simply that the distance that the ball is 78.4 meters from where it started. Okay? This must be a pretty tall cliff or something that we dropped this ball off of to allow it to fall for 4 seconds. Okay? If we had wanted to define direction, upward direction as positive, then we would revisit this and put a negative sign here for our g. But we didn't have to do that for this problem since it wasn't necessarily specified. Okay? Let's have a follow-up to this. How long will it take the ball to fall 120 meters? So if we knew that our cliff was a total of 120 meters tall, how long would it take for the ball to reach the bottom of a 120 meter cliff, or just to fall 120 meters? Okay? We can use the exact same equation now. And because now we've swapped out what we know. Now what's known is the y, or x, okay? Again, the gravity and the initial velocity. And what we want is now the time. So we can simply solve the exact same equation, but for time. And this will work out nicely in this case because that initial velocity was 0. The occurrence of time here is going to drop out. It's going to be canceled. So we have then 1/2 9.8 meters per second squared times that t squared. So I substituted in my y of 120 equals initial velocity 0 times time, which I don't know. That's all going to equal 0 though. So this simplifies a little bit, right? To 120 equals 4.9 times t squared. So we would divide by the 4.9, okay? And then we would take the square root of it. So t is going to be the square root of that 120 over 4.9. I didn't calculate what that is, sorry. Actually, I did. It's 24.5, sorry. 120 divided by 4.9 is 24.5. And so the square root of that is 4.9 seconds. So it would take the ball 4.9 seconds to fall from whatever its initial position was down 120 meters there. Okay? Again, if we think about the signs, if for some reason, if direction had been defined, if this was 0 position that our person was at, and this was negative 120, right, down, then we would have used negative for gravity, but those two negatives would have canceled out. Like if we had gone back and put in a negative here and a negative there, you see they would have just reduced each other back to being a positive value. All right? Because you have to get a positive time. So if the signs ever give you trouble, think about things that you know have to be positive. And time is one of those parameters that always must be positive. Okay? All right, let's do another one. Switch up to another set of examples here. Okay. Again, we have a ball. Okay. This time, our ball is thrown upward. Okay, so thrown upward from an initial height of 14 meters with in initial velocity of 3.6 meters per second. At what total height, I put total in parentheses there, I'll explain that in a second. At what total height is the ball after 1.2 seconds? Okay. So again, that idea of total, we talked a little bit about this last class. These equations, especially for position, are just telling us how far the object moves during a certain amount of time. If we want to know its actual position, we need to know where it began. So these are more like delta y or delta x, right? And so, you know, a good visual here would be that the ball is, again, released going upwards like that, okay, at an initial height. If this is 0, here's your 14 meters, okay? The ball is released 14 meters above the 0 point. This is now defining some direction, you know, that this is the positive direction for y, okay? Which means that gravity is acting downward in a negative fashion. Okay, so a little image here will help us understand the signs, right, that we need. Okay, so this ball, depending on how long it's in the air, may go up, and it may even come back down past us this way. All right. Okay, so what do we know? What's known is the initial velocity, gravity, okay, and the time. Don't think that this 14 meters is the position. That's just the, again, because this isn't really the position. This is the distance that the object travels or moves if we have these equations here. All right? But that is the equation that we need. When we know initial velocity, gravity, and time, we can find distance, all right, using the initial velocity times time plus 1/2 gt squared. Okay? So this time we would have numbers for the initial velocity, 3.6 meters per second times 1.2 seconds plus 1/2 negative 9.8 meters per second squared times 1.2 seconds squared. Okay? And it's really important that we have the negative on gravity now, because gravity is acting opposite to the direction that the ball is initially going with its velocity. Its initial velocity is upwards, and gravity is acting to change that velocity, to change the direction of the velocity and speed. Okay? But once we plug all this in, we get 4.32 minus, it looks like, 7.06. So our y is negative 2.74 meters. Again, this is, you want to remember, relative to the initial position. Right? This equation is the distance traveled, okay, or the distance relative. So in this case, the ball has actually gone all the way up and come back down past, as I showed, the person throwing it. Okay? So the real position is going to be 14 minus the 2.74, all right, or 11.26 meters above the ground. Yep. So this is 11.26 meters. Okay. All right. Let's do one more example, following up on this same one here. Okay. And the follow-up question would be, how long will it take for the ball to reach the ground? Okay. So there again, we need to do an inventory of what we know and what we want. So if we're asking now about how long it'll take the ball to go, up from our hand and then come back down and reach all the way down to the ground, okay? Now we know some slightly different parameters. We still know the initial velocity. We still know the the acceleration due to gravity. And now we know the y value, okay, the relative position where this is going to be. And so we want time. So we actually have the same 4 properties between these two examples here. It's just that we've swapped out knowing. Instead of knowing time, trying to find position, now we know the position and we want to find the time. So we're going to go ahead and use the exact same equation here. Okay. You may look at some of the other equations of motion and choose to use one of them as well. I'm going to show you this one, though, in particular to make sure we understand how to use the quadratic equation, which we occasionally have to make use of. All right? So how are we going to get to that? So the y is negative 14, right? Because relative to where we started, again, if this is, now if we think of this as 0, okay, or even if this is 0, the ball has come down 14 meters from its original position, okay, if you define that as 0, okay? Either way, you're going to get the same answer. If you define this as 0, you can see that you're 14 meters below it. If we define this as 0, you started 14 meters up above it, and again, you've come, the final stopping point of the ball is 14 meters below where it began. All right, so that's why y is negative 14. The initial velocity was still a positive upward moving 3.6 meters per second times time, which we don't know, plus 1/2 times negative 9.8, gravity is acting in the downward direction, times t squared. This is going to lead to, as I mentioned earlier, a polynomial, a second-order polynomial, commonly thought of or called a quadratic. There's nothing to be scared of. They're really common, particularly in equations of motion. All right? We shouldn't be worried about this. We just need to be careful and understand what the rules are here. So when you have a quadratic equation, you're trying to get it into the form 0 equals ax squared plus bx plus c. All right? A being your coefficient of your squared, okay, variable, x, and b being the coefficient of x, and then c being the y-intercept. In this case, t is our x, our independent variable, or what we're trying to find in this problem here. Okay? So, I'll do a couple extra steps this first time for you. This would be negative 14 equals 3.6t minus 4.9 t squared. So you don't have to, but a lot of people like to have that a value being positive. So I'm going to bring the terms over to the left side. So I would add 4.9 t squared, subtract 3.6t, and then I still have unchanged, the negative 14. So that equals 0. So 4.9 is my A, negative 3.6 is my B, and negative 14 is my C. How do I use these to find the value of time? We need the quadratic formula. If we don't have a polynomial that we can factor, learning the methods that you probably learned in an algebra class in middle school or high school, then we have to use the quadratic formula, which tells us that x from the A, B, C version there is equal to negative b plus or minus the square root of b squared minus 4 times A times C all over 2A. All right? So we're substituting in the values that we've identified as these coefficients, A, B, and C. So for this, that would end up being positive 3.6, because it's the negative of negative 3.6, plus or minus the square root of negative 3.6 squared minus 4 times 4.9 times negative 14. All that's going to be divided by 2 times 4.9, 2A. Right? This will lead to two potential answers, because in one case you're going to take 3.6 plus this square root term, and in another case you're going to take 3.6 minus that. And then each of those respective values would get divided by the 9.8, the 2 times 4.9. Okay? So when I do that, and I want you to encourage you to try these calculations, I get 2.1 seconds or negative 1.4 seconds. As I mentioned earlier, time is a quantity that really has to be positive. So we know that the ball is not at this position 1.4 seconds before we released it, before we started our stopwatch. That means that 2.1 seconds is the answer. Okay? You could do a check of this if you wanted to, by the way. You could take the time 2.1 and come back to the previous example that we did and figure out what's the distance that the ball has traveled relative to its starting position in 2.1 seconds. And if you plugged in 2.1 for a time here, you would predict y equals negative 14. The ground, in other words, which is negative 14 meters from where the ball began. Right? So that is vertical motion, or gravity and free fall motion. The next step from here is to consider motion in 2 dimensions simultaneously. All right? Problems up to this point, we've only been considering one direction of motion, x or y. Now we're going to move into what's classically just known as projectile motion, where an object has both x and y trajectories, okay, or movement, all right? And these are no more difficult, to be honest, than the problems that we've been doing. They're just more work because you have to work with both directions, but independently of each other. We have to use some equations to describe what's happening in the x, and then we have to separately use equations to figure out what's happening in y. Depending on the type of problem, you might need to use one, perhaps like a y, how long the object is falling maybe, right? To then determine an x property, how far an object might go in the x direction, right? So that'll be what we pick up with in our next class, and what we're going to finish out in Chapter 6 for. All right? This has been a pretty good set today. I'll have posted into Moodle the list of practice problems for you to be working on. Of course, I gave out a homework assignment, Chapter 6 worksheet. for Chapter 6. That's due Friday, September 29th. All right? And so a few of the problems are very similar to what we've done today for gravity and free fall. And then the remaining problems will be associated with projectile motion. So you'll be able to finish them after our next class period. Thanks for tuning in today. Saved us a little bit of time. Looks like we're coming up about 10 minutes less than a typical class. So enjoy that little extra bit of time. And I'll see you in class on Wednesday. Have a good day until then.